Well, hello there. It's a pleasure to have you here. Go ahead, pull up a chair. Let me pour you a cup of coffee. The name's Rod, and I've spent more years with my head in the clouds than most folks have spent on solid ground. I've seen sunrises paint the curvature of the earth from 40,000 feet, and watched thunderstorms build into magnificent, terrifying castles of vapor from a safe distance. Through it all, my constant companions have been the magnificent machines that make flight possible. I'm not just talking about the wings and the fuselage, but the very heart of the modern airplane, the jet engine. It's a symphony of controlled explosions, a marvel of engineering that still gives me goosebumps. Many young pilots today jump right into glass cockpits and computerized flight plans. They know which buttons to push and they know them well. But sometimes I wonder if they truly feel the soul of the machine they command. Do they understand the beautiful violence happening just behind their seat? To truly master an aircraft, you need to understand what gives it life. It's like knowing your dance partner's every breath and heartbeat. For me, that deep understanding began with learning about the different kinds of jet engines. Each one has its own personality, its own strengths and its own little quirks, just like the pilots who fly them. Over my long career, I've had the privilege of flying behind several of these incredible engine types. I felt the raw, unadulterated shove of a pure turbojet and the steady, reassuring pull of a turbofan on a long-haul flight. I've even spent some time with the unique hum of turboprops. Each experience taught me something new, not just about physics and mechanics, but about the art of flying itself. These engines aren't just lumps of metal. They are characters in the grand story of aviation, and I'd like to share some of those stories with you today. So, let's get into it, shall we? Let's talk about what makes these metal birds sing. My goal here isn't to bury you in complex diagrams or mathematical formulas that would make your head spin. No, I want to talk to you like I would to a new co-pilot on a long, quiet night flight over the Pacific. We're going to break down each major type of jet engine one by one. We'll discuss how it works in simple terms, where you're most likely to find it, and what its limitations are. Think of this as a hangar talk session where the old-timer shares a few secrets from his logbook. By the time we're done, you'll look at the sky a little differently, I promise you that. Let's start our journey with the engine that started it all, the turbojet. This is the original, the pioneer, the one that made Sir Frank Whittle and Hans von Ohain household names in aviation circles. Flying a plane powered by a pure turbojet is an experience you never forget. It's loud, it's thirsty, and it feels like you're being pushed by a giant invisible hand. The principle behind it is beautifully simple, really. It's Newton's third law in its most exciting form. For every action, there is an equal and opposite reaction. The engine throws a massive amount of hot gas out the back and the plane rockets forward. So how does this beast work its magic? Imagine a big tube that's open at both ends. At the front, it sucks in a huge gulp of air. This air is then squeezed by a series of spinning blades called a compressor, making it very dense and hot. This compressed air is then forced into a combustion chamber, where it's mixed with a fine spray of jet fuel and ignited. Boom! This creates a powerful explosion and a rush of superhot gas. This gas blasts through another set of blades called a turbine, making it spin like a pinwheel in a hurricane. This turbine is connected by a shaft back to the compressor at the front, keeping the whole cycle going. The rest of the hot gas then screams out the nozzle at the back, creating that powerful thrust. You don't see many pure turbojets around these days, especially on commercial airliners. Why? Well, they have their limitations. Their biggest drawback is their fuel efficiency, or rather their lack of it. They drink fuel like a sailor on shore leave, especially at lower speeds and altitudes. They are also incredibly noisy. The roar of an early turbojet taking off was something to behold, a sound that would rattle your bones and set off every car alarm in a 5-mile radius. This made them less than ideal for flying over populated areas and led to strict noise regulations that effectively retired them from mainstream commercial use. They were the rock stars of their day, but a bit too wild for the modern world. Despite these limitations, the turbojet was a game changer. It powered the first generation of jet fighters like the F-86 Sabre and the MiG-15, and early jet airliners like the de Havilland Comet. Its design also laid the foundation for every other jet engine that followed. It was the crucial first step that took us from propellers to the jet age. You might still find them on some high-speed military aircraft or drones, where their simplicity and high-speed performance are valued more than quietness or fuel economy. The turbojet may be a relic of a bygone era, but its legacy is written across the sky every single day. Now let's talk about the engine you've almost certainly flown with, the turbofan. If the turbojet was the wild rock star, the turbofan is the polished, professional studio musician who sells millions of records. It powers nearly every modern airliner, from the little regional jets to the jumbo A380s. When you look at the engine on the wing of a Boeing 737 or an Airbus A320, you're looking at a turbofan. It's the undisputed king of commercial aviation, and for very good reasons. It took the brilliant idea of the turbojet and refined it, making it quieter, more powerful, and vastly more fuel efficient. It's the reason you can fly from New York to London without having to refinance your home. The secret to the turbofan's success is a simple but ingenious addition, a great big fan at the very front. This fan is much larger than the opening of the engine core behind it. When the engine is running, this fan moves a colossal amount of air. A small portion of this air, maybe 10 to 20%, goes into the core of the engine, which is essentially a small, highly efficient turbojet. It gets compressed, burned with fuel, and used to spin the turbine, just like we discussed. But here's the clever part. The turbine doesn't just power the compressor, it also powers the giant fan at the front. The vast majority of the air, the other 80 to 90%, bypasses the core completely. It just gets accelerated by the fan and flows around the outside of the engine. This bypass air is what makes the turbofan so special. Most of the engine's thrust actually comes from this cooler, slower moving air being pushed by the fan, not from the hot jet blast coming out of the core. This is a much more efficient way to move an airplane. Think of it like the difference between trying to paddle a canoe with your hands versus using a large paddle. The large paddle moves more water more slowly, and it's a lot less work. This bypass air also acts as a blanket of sound insulation, wrapping around the noisy jet core and making the engine significantly quieter than a pure turbojet. This is why a modern A350 taking off is a gentle whoosh compared to the deafening roar of an old 707. Of course, nothing is perfect, and the turbofan has its own set of trade-offs. The large fan and its casing add significant weight and diameter to the engine. This increased size creates more drag, which can limit the aircraft's top speed. While a turbojet is happiest screaming along at supersonic speeds, a high bypass turbofan is most efficient at the subsonic speeds where airliners cruise, typically around Mach 0.8 to 0.85. For the world of commercial travel, this is a compromise we are more than happy to make. The incredible gains in fuel efficiency and noise reduction far outweigh the limitation on top speed for carrying passengers and cargo around the globe. Now, let's step away from pure jet propulsion for a moment and talk about a clever hybrid, the turboprop. Don't let the propeller at the front fool you. The heart of this machine is a true jet engine. I've flown my share of turboprops, like the rugged King Air and the dependable Dash 8. They have a distinct sound, a high-pitched hum mixed with the familiar thrum of propeller blades slicing through the air. These aircraft are the unsung heroes of regional travel, cargo hauling and utility work. They're tough, reliable and incredibly efficient at what they do, which is flying at lower altitudes and shorter distances. So how does a turboprop work? It starts out very much like the turbojet we talked about. Air is drawn in, compressed, mixed with fuel and ignited. This creates a blast of hot gas that rushes towards the back. But here's where the turboprop takes a different path. Instead of using that gas blast primarily for thrust, it uses almost all of its energy to spin a turbine. In fact, a turboprop has an extra set of turbines designed to extract as much power as possible from the exhaust gases. This spinning turbine is then connected to a gearbox, which slows down the incredible rotation speed to something a propeller can handle. The propeller then bites into the air, creating the thrust that moves the airplane forward. The main advantage of this setup is phenomenal efficiency at lower speeds and altitudes, say below 30,000 feet and under 400 miles per hour. In this flight regime, a propeller is simply better at converting engine power into thrust than a pure jet exhaust. This is why you see turboprops operating out of smaller airports and on shorter routes where they spend a lot of time climbing and descending. They can get into and out of shorter runways and burn significantly less fuel than a regional jet on a 300-mile flight. This makes them economically perfect for connecting smaller communities to major hubs. The primary limitation of the turboprop is, unsurprisingly, the propeller itself. As the aircraft's speed increases, the tips of the propeller blades can start to approach the speed of sound. When this happens, shock waves form on the blades, causing a massive increase in drag and a dramatic loss of efficiency. This effectively puts a speed limit on turboprop aircraft. While some very specialized military designs have pushed this limit, most turboprops are content to cruise at speeds well below what a turbofan-powered jet can achieve. For the missions they are designed for, however, this isn't a limitation, it's just a characteristic of their excellent design. Let's now turn our attention to the whirlybirds. If you've ever been near a helicopter, you've heard that distinctive thump, thump, thump of the main rotor blades. But have you ever wondered what's spinning them? In most modern helicopters, from the nimble Bell 206 news chopper to the mighty CH-47 Chinook military transport, the power comes from a special kind of jet engine called a turboshaft. This engine is a close cousin to the turboprop we just discussed, but instead of turning a propeller to push the aircraft forward, its job is to turn a transmission that spins the helicopter's rotors. It is the powerful, compact heart that gives these amazing machines their vertical lift capability. The inner workings of a turboshaft are almost identical to a turboprop. It has an intake, a compressor, a combustion chamber, and a set of turbines. Just like the turboprop, its design is optimized to extract as much energy as possible from the hot exhaust gas and convert it into rotational power or shaft power rather than producing direct thrust. The hot gases spin the turbines with incredible force, and this power is sent out through a shaft. This output shaft isn't connected to a propeller but rather to a complex helicopter transmission and rotor system. This system then directs the power to spin both the main lifting rotors and the smaller tail rotor, which keeps the helicopter from spinning out of control. The biggest advantage of the turboshaft engine is its incredible power-to-weight ratio. Piston engines that are powerful enough to lift a heavy helicopter would be enormous and far too heavy. A turboshaft, on the other hand, can produce a massive amount of horsepower while being relatively small and lightweight. This is absolutely critical for helicopter design, where every pound of weight saved in the engine is another pound of fuel, passengers or cargo that can be carried. Their smooth operation and reliability are also major selling points. A sudden engine failure in a helicopter is a far more critical emergency than in a fixed-wing airplane, so the dependability of these jet-based engines is paramount. The main limitation of a turboshaft engine is similar to its cousins. It is most efficient when running at a high, relatively constant speed. Helicopter rotors, however, need to change their speed and pitch constantly to maneuver. This is managed by the complex transmission and rotor head, but it means the engine itself is not always operating at its absolute peak efficiency point. They also consume a considerable amount of fuel, which is why a helicopter's range is often much more limited than that of a fixed-wing aircraft of a similar size. Despite this, for any application that requires a machine to hover, lift heavy loads vertically, or land in tight spaces, the turboshaft engine is the undisputed champion. All right, now we're getting into the really exotic stuff, the kind of engines that push the boundaries of what's possible. Let's talk about the ramjet. You won't find this on any commercial airliner or your friendly neighborhood helicopter. Ramjets are built for one thing and one thing only: pure, blistering speed. They are the engines of high-speed missiles and experimental aircraft designed to fly several times the speed of sound. The beauty of the ramjet lies in its almost absurd simplicity. It has no moving parts, no compressor blades, no spinning turbines. It almost looks like a fancy hollow pipe. It's a testament to the idea that sometimes the most elegant engineering solution is the simplest one. So how can an engine with no moving parts possibly work? The magic is in the name ramjet. A ramjet can only work when it's already moving at very high speed, typically above Mach 2 or twice the speed of sound. At these speeds, the air rushing into the engine's specially shaped inlet is rammed and compressed by its own forward motion. This is called ram compression. The shape of the inlet slows the supersonic air down to subsonic speeds, which dramatically increases its pressure and temperature, just like a mechanical compressor would, but without any moving blades. This highly compressed air then flows into the combustion chamber, where fuel is injected and ignited, creating immense heat and pressure. The resulting hot gas then blasts out the nozzle at the back, generating powerful thrust. The advantage of this design is clear. With no complex, heavy and delicate turbo machinery like compressors and turbines, the ramjet is lightweight, simple, and can operate at speeds and temperatures that would melt a conventional turbojet. A turbojet's rotating blades have a speed limit, but a ramjet can theoretically keep accelerating as long as its structure can handle the heat and pressure. This makes it the perfect engine for sustained, high-Mach flight, which is why it's the preferred choice for long-range air-breathing missiles. It's an engine that truly comes alive when it's already screaming through the upper atmosphere. The most significant limitation, of course, is that a ramjet cannot produce any thrust when it's standing still. It's completely useless on the runway. An aircraft powered by a ramjet needs another type of engine to get it up to the necessary speed for the ramjet to take over. This is often a rocket booster, which accelerates the vehicle to Mach 2 or 3 and then falls away, or a more conventional turbojet engine that is used for takeoff and initial acceleration. This requirement for a separate propulsion system adds complexity and weight to the overall vehicle design. Ramjets are also very inefficient at lower speeds, making them highly specialized tools for a very specific high-speed job. If you thought the ramjet was fast, let me introduce you to its even more extreme older brother, the scramjet. The name stands for supersonic combustion ramjet, and that little bit of extra text makes a world of difference. While a ramjet slows the incoming supersonic air down to subsonic speeds for combustion, a scramjet is designed to keep the air flowing at supersonic speeds throughout the entire engine. This is a concept that seems to defy logic. It's like trying to light a match in a hurricane and then keeping it lit. This is the absolute cutting edge of air-breathing engine technology, designed for hypersonic flight, speeds of Mach 5 and beyond. The principle is an evolution of the ramjet. The vehicle is already traveling at hypersonic speed, say Mach 6. Air enters the inlet and its shape compresses the air, but not enough to slow it below the speed of sound. This supersonic, highly compressed air then flows into the combustion chamber. Here, a special fuel like liquid hydrogen is injected, and it has to mix with the air and combust in a matter of milliseconds as it blasts through the chamber. The resulting release of energy from this supersonic combustion accelerates the flow even further, and it exits the nozzle at an even higher hypersonic speed, producing thrust. The entire process is mind-bogglingly fast. The primary advantage of the scramjet is its potential for incredible speed. By keeping the airflow supersonic, it avoids some of the temperature and pressure issues that limit the top speed of a ramjet. In theory, a scramjet-powered vehicle could fly at speeds of Mach 15 or even faster within the atmosphere. This opens up incredible possibilities, like being able to fly from New York to Tokyo in about 2 hours, or creating a new generation of reusable space launch vehicles that can fly most of the way to orbit before a small rocket motor kicks in. Because it uses oxygen from the atmosphere, it doesn't have to carry heavy liquid oxygen like a rocket does, making it far more efficient for atmospheric flight. As you can imagine, the limitations are immense. Scramjets are even more finicky than ramjets. They only start to work at very high hypersonic speeds, perhaps Mach 5 or higher, meaning they need a significant rocket booster to even get started. The engineering challenges are monumental. The temperatures and pressures inside the engine are so extreme that they can melt the most advanced materials known to man. Fuel injection and combustion must happen in the blink of an eye. At the moment, scramjets are purely experimental, powering unmanned test vehicles like the NASA X-43. We are still many years and likely decades away from seeing them used in any practical everyday application. Finally, let's talk about the one engine on our list that is not, strictly speaking, a jet or air-breathing engine at all, the rocket. I include it here because it's a critical part of the high-speed story and a marvel of propulsion. From the mighty Saturn V that took us to the moon, to the solid rocket boosters on the space shuttle, to the engines that power SpaceX's Falcon 9, rockets are our ticket to leaving this world behind. Unlike every other engine we've discussed, a rocket does not need to breathe air from the atmosphere. It carries its own oxygen, usually in liquid form, called an oxidizer, along with its fuel. This is the key difference that sets it apart. The way a rocket works is the essence of Newton's third law. Inside the engine, the fuel and the oxidizer are mixed together and ignited in a combustion chamber. This creates an unbelievably powerful and hot explosion. The resulting gas is funneled through a specially shaped nozzle called a de Laval nozzle, which is designed to accelerate the exhaust gases to extremely high velocities, often several times the speed of sound. This massive expulsion of gas out the back creates an enormous amount of thrust, pushing the rocket forward, or in most cases, upward. It's a simple principle executed with incredible power and precision. The rocket's greatest advantage is its ability to operate anywhere, including the vacuum of space. Since it carries its own oxygen, it doesn't care if there's air around it or not. This is why it's the only engine capable of getting a spacecraft into orbit and beyond. Rockets also produce a tremendous amount of thrust for their weight, far more than any air-breathing engine. This is why you need them for the initial brute force job of lifting a heavy vehicle off the launch pad and pushing it against the relentless pull of Earth's gravity. For pure, unadulterated power, nothing beats a rocket. The main limitation, however, is its colossal inefficiency. A rocket has to carry all of its propellant, including the heavy oxidizer, which makes up most of the weight. It consumes this propellant at an astonishing rate. A large rocket can burn through tons of fuel and oxidizer every single second. This means its burn time is very short, usually only a few minutes. This is why rockets are used for short, intense bursts of acceleration, like launching into space, or as a booster for a ramjet vehicle. Using a rocket for a long-distance flight within the atmosphere would be like trying to cross the ocean in a drag racing car. It's the wrong tool for the job. So there you have it. We've journeyed from the noisy, pioneering turbojet to the sleek, efficient turbofan that carries us across continents. We've looked at the workhorse turboprops and the helicopter's turboshaft heart, and we even ventured into the exotic high-speed world of ramjets, scramjets, and the pure power of the rocket. Each one is a marvel of human ingenuity, a solution tailored to a specific challenge in the eternal quest to conquer the skies. Understanding them, even at this simple level, gives you a deeper appreciation for the incredible technology that we so often take for granted when we buckle our seatbelts and settle in for a flight. As a pilot, knowing your engines isn't just academic, it's about respect. It's about understanding the sounds, the vibrations, and the subtle changes in performance that tell you a story. It's the difference between being a driver and being a true aviator. Whether it's the gentle hum of a turbofan at cruise altitude or the powerful roar on the takeoff roll, that engine is your partner. It's a relationship built on trust, knowledge, and a healthy dose of awe for the physics at play. I hope this little hangar talk has sparked a bit of that awe in you too. The next time you're at an airport, take a moment to really look at the engines on the wing. See that giant fan at the front of the turbofan? Now you know that most of the air it moves is bypassing the core, making your flight quieter and more efficient. When you see a smaller plane with propellers on a regional ramp, you'll know that a powerful jet turbine is spinning those blades. The world of aviation is filled with these incredible details, And the more you learn, the more fascinating it becomes. It's a journey of discovery that never really ends, and I've been on it my whole life. I've enjoyed sharing a few pages from my mental logbook with you. The sky is full of stories, and the engines are the ones that write them. If you enjoyed this little flight through the world of jet propulsion and want to learn more about the amazing technology that makes modern aviation possible, then I encourage you to keep exploring. For more easy-to-understand insights and deep dives into aviation tech, make sure to follow and subscribe to my friends over at Aviation Tech Zero. They do a fantastic job of keeping the spirit of learning and discovery alive. Until next time, keep your eyes on the skies. Clear skies and tailwinds to